Hi, how are you? Thank you for coming. Thank you so
Yeah,
much.
yeah. Hi, I'm Pedram. Um,
Yeah, nice to meet you. I'm Katarina.
Nice meeting you. It's my first time in here. Let's see. Um, I also emailed you some slides which could help. I didn't know what how this forum is. Is it is we are not sharing pictures or we are?
We
It's not a video call, right?
No, it's not a video call, but we can add the slide as a link. So let me do that. I just saw that you just emailed me.
Yeah, it's
So
a
let
PDF
me.
file.
Yeah,
And
I'll if that's okay with you, I'll add it to my Google Drive and then
yeah, sure.
make it
These are
shareable.
yeah.
Okay, let me just do that really quick and meet Serena. She's one of our moderators here. She's also quite interesting researcher herself. And then Dennis and Victoria. Please meet Pedram and Dr. Roushan. I hope I'm saying your name right.
Yeah, yes, good. Yes, thank you. Yeah,
Okay.
that's good.
Okay.
Hello.
Hi,
Yeah.
Hello.
hi.
Pleased to meet you, Doctor.
Nice meeting you guys. Yeah, we can. Okay, we can get. Well, let's get the time arrive, and then
Yeah.
maybe you tell me about.
About the Science Society.
Yes.
And
Yeah, and what is its relation with NYU or?
well, I'm at NYU and I'm also working at the company 3D Bio. So um uh so in the email I just introduce myself, like what I do. But in general, this year kind of I started using Clubhouse during the COVID shutdown, more or less. So and people used to invite me into rooms to talk about things that I know of and things that I don't know about. Just because I'm a scientist, I don't know about everything.
You're right.
So what
Yes.
I started doing was to say, I don't know. Let me see if I can invite the scientist that actually knows about the subject and share with you. And it's kind of turned into a thing. And then I created this club here on Clubhouse to do it more regularly and to discuss like interesting science topics and to give people the opportunity to interact with the scientists. So yeah, so that's how this started. It was like probably it started out of boredom during COVID, and now it's became a bigger and bigger club and a quite friendships and science interested and enthusiasts come here and geek out basically.
Okay, I understand. Yeah, sure. So, but the group of people who usually join, uh, well, they are usually scientists. Do they have some science background, or how does it work?
It's a mixed bag. Some of the folks on stage are trained in science, and some of the folks in the audience are also trained, but also there's a lot of folks who tune in just to listen to the nerd hour.
I see. Uh, okay, and then what is the stage and what is audience? So some are on the stage. Okay, that's the lingo.
So for those who are on the stage, they can unmute their microphone and speak.
I see.
For in the audience, they can raise their hand and a moderator can bring them up on stage to ask more questions.
Gotcha. Okay.
And they can also participate in the chat
You see,
on the.
because I work for Google, people usually assume I know things about computers and apps and whatnot. It's a mind boggling how little I know and how I get confused. I had to talk with someone to make a printer last night to make some sense. I need to install something for printer, and that became a whole 1 hour thing. It's unbelievable how bad I can be. Seriously, uh, that's what I keep asking. Try to get the sense of how these things are set up.
Well, another thing about Clubhouse is you can click on anyone's picture and see their bio, and many of us have written more detail about our backgrounds, so it's a good way to get a feel for who you're talking to or so forth.
Well, okay, I see. Science through visual arts. Okay, yeah. Uh, yes, that's interesting. Okay.
Anytime you have a question, feel free to ask it. Many of us have been on Clubhouse for some time, so we probably have some insight.
Many of
Sure.
us here and have been on Clubhouse longer than we like to admit.
Okay, I see. I see. I see. Okay, yeah, I'm at your service. It's 6 o'clock. Let's get
Victoria,
going.
would you like to ask the opening question?
Let me start by welcome everyone to the Science Society. We are very honored to have our guest speaker here today, Dr. Pedram Roushan. He's a senior scientist at Google, and let me tell him a little bit about him. So he did his education, and I'm not sure if I'm saying it wrong, at the Baha'i Institute
Yes.
for Higher Education.
Yes.
And it was founded in 1987, and in the response to Iranian's government's continuing campaign to deny Iranian Baha'is access to higher education. And I found what you wrote about it, and I really found it was such an impressive statement of yours about the institute. Uh, I
Thank
have
you.
a lot of very warm feelings about my home institute in Portugal and my advisors there. So they created this very special program also. So I share your sentiment about that. And he graduated from by IHE in civil engineering in 2000, and he continued higher education in the United States and studied physics. He did his PhD in 2011 at Princeton University, and he performed the first scanning tunneling microscopy on the surface of topological insulators in the lab of Yazdani. And he did 3 years of postdoctoral studies in the Martinis lab at the University of California, Santa Barbara. And then in 2014, he joined the Google Quantum Hardware Lab, and then aiming on making a quantum computer. And with the Google team in 2019, they performed the first computation on a quantum processor beyond the capability of a supercomputer. So yeah, we are very honored to have you. And Victoria usually asks more general questions in the beginning, so the audience gets to know also you as a scientist a little bit better. I hope that's okay with you, and then we'll give you the stage for your presentation. That it's a pin to the room on the top.
Sure,
Thank you.
sure. Yes. Yeah. Fantastic. Yes. Let's make it question based rather than me going on some tangent and keep talking. Yeah. Uh, if there's no question, I can start, but maybe it's much better to have a question to begin with.
Oh, we always have questions. Thank
That's
you, Dr.
fantastic.
Especially when we receive not only such interesting research, but such a fascinating and detailed bio that you'd sent. And I'm always interested in hearing about what path led people to their particular field of research. and how you found yourself interested in science in the beginning. And I recognize that that could be a broad question, so I leave it to you to answer as you know as you wish.
Yes, sure. I was born in Iran in 1977. So when we grew up and when I became teenager, it was the the options or the activities were very limited. You can imagine the media was very much um, limited in showing pictures of the West or something. So the options or things that comes to mind was very limited. But I fall in I fall in love with mathematics. You know, Iran doesn't have the strong infrastructure to support experimental physics, doesn't have the structure to have good laboratories for high school or so. But then mathematics become very big. Um, you can imagine maybe similar to Russia. And you know, math books, besides the classroom books, became my interest during my teenager years. So when I got to then, as was mentioned, Baha'is, which are a minority living in Iran, religious minorities, have been denied access to higher education. So in 1987, they start their own university. There are maybe 500,000 Baha'is in Iran. So they start their own Institute for Higher Education. They call it BIHE. You can learn about it more by looking online resources. And there, I couldn't continue science. I start doing civil engineering. There was very limited options. And I think maybe 1996 to 2000, I did civil engineering there. But then when I came to United States and University of Pittsburgh to do another undergraduate degree, I was really into physics and mathematics, both. I didn't know which one fascinates me most. You know, there is a right time and right age. If you read about quantum mechanics and whatnot, it's impossible not to fall in love. It's impossible not to be perplexed and bewildered and think that spending life on it is really interesting life. I just had it with me from my early 20s. And then when I came here, I start math and physics at the same time at the University of Pittsburgh. Math was, to be honest, was a bit abstract and a little beyond my intellectual level. So I figure out experimental physics is something I can do. I worked in an experimental lab at University of Pittsburgh, Western Pennsylvania. Then I moved to Princeton. I got closer to New York, um, uh, and then I was become an experimentalist. And just the fascination that you can do something and you can answer a question which is deep, and no one knows the answer before you. You know, you can now you have a very unique privilege of knowing something that no one knows, and it has some value to it. It's just fascinates me, and I managed, or I was lucky enough to be able to stay in science for my 20 years that I have been in the United States. And but I think I've been very much driven, even the years that science was denied from me in Iran. I could not participate in any government state university. All the universities, in fact, run by the states in Iran. So I had to go to this so-called underground university, this Baha'i community-sponsored university, and it studied civil engineering. But mathematics and physics was always uh, with me, and was always my passion.
I think that we are all grateful that there is the answer to the challenge, to the socio-political challenges in Iran, that there is such an answer as the Baha'i Institute of Higher Education. And I was interested also to read that the professors are volunteer there, and I don't know if that's still true.
For the most part, is true. For the most part, well, okay. So this started in when after revolution, it became very obvious that Baha'is cannot go back to university. They shut the universities down. They had a cultural revolution. They wrote this constitution for cultural revolution. And then during that years, they made it clear that Baha'is cannot go back. So it took Baha'is to fight back for a few years, but then they realized the best option is to start their own institute. That took maybe 8 years after revolution. And I joined this institute in its 10th year or so, 10 years into it or 8 years into it. And those years, yes, we had to go to people's houses to study calculus, study chemistry. But I like the people in here to realize this is Iran of 1980s, Iran of 1990s. There's no personal computer. There's no YouTube. When they don't let you to go to university, the only way to learn linear algebra, calculus, chemistry, physics is close to you. This is, please remember that. There's a book and there's a teacher. This is 80s and early 90s. When I left Iran, still there was no personal computers, very, very few. That was 1999. And this was more or less the case everywhere, right? There was no vast amount of YouTube videos and PDF of the books online. If they close the door of the university, then if you don't have access to the best teachers, the best university education, then you're done. There's not that much alternatives. And Baha'is try to show resilience toward that, show some constructive resilience by starting their own institute, finding the professor who fired from their job, trying to form a underground, so-called underground, and of course not physically underground, but conceptually underground university, and offer these courses. So in people's houses. So imagine Tehran is a large metropolitan, and we had to go take a course in statistical physics or statistics one corner of Tehran, and then take a cab and go to the other side of Tehran to take a class to go to someone's house and then take a class in physics or mathematics or calculus or something. So so now that I look back at it, now that I received education in several institutes in the US, I can go back and look at it. It was not the quality of the courses that mattered. It was not the best linear algebra teacher and whatnot. You can imagine that. But it was just the approach toward the education that made an everlasting effect on me. It was how valuable learning of science was for this community and for us, that we had to do it at all costs. And this was really has been with me since then, I think. This was what I gathered from that institute. Of course, the quality of education, you can imagine that Princeton is better than Pittsburgh, and Pittsburgh better than BIHE. But what BIHE had to offer was this very unique angle of view at education itself and at science itself.
Thank you for, this is really an exciting tour into what you've experienced, and I think probably many of us will go back and have to do research into really what was happening in Iran and at that time, and also to learn more about Baha'i Institute of Higher Education. And I just want to say, I feel like that what's really come out of that, you mentioned the value of learning, and what I read about the professors and their methods of education, that's really but that was maybe, I don't want to say liberating for you, because that desire, that creative desire is innate. But I heard you say that you felt that experimental physics was less abstract than mathematics, and so that helped you decide your path. And that's the kind of thing that you really need an open mind and love for learning to be able to,
Yes.
to explore.
Yes.
So thank you so much for
Sure.
allowing me to ask you some questions.
Yeah, sure.
Yeah, if you would like to switch now over to the presentation, please go ahead. Thank you.
Yes, so you guys can open the PDF file. Um, I I had a little busy day, so I had to cut pieces from one of my talks. Uh, oh shoot, it says October 2021, but yes, anyways, it's pieces of variously comes together. So here you see a picture of a superconducting chip. It's maybe about an inch, the square, the bigger square that you see, the colorful square is a is about 1 inch of aluminum. And this processor is something we use to do computation. And in the first few slides, I try to tell you about that. If we go to the second slide, you so people can do it themselves. Is that correct?
Correct. They can click on the link and then follow along. Yes.
Right. Sorry, this was an animated slide. Now I don't think I shared PDF, so you see things on top of each other. You see a picture of our team. It's about 60 people. This is in a rooftop of Google building in Los Angeles right before the COVID time. Right, I think when we are celebrating publication of this work that you see in here. This is 2019, and we wrote a manuscript which is try to show the power of quantum computations and how it exceeds beyond classical computations or the other means of calculations and computations that we know. This article is open access. You can read it yourself. We put very much energy into it to be sure it's readable uh, by people who are not expert in the subjects. It's been highly cited. You notice is much more cited than an average article, because we consider this as a very big turning point for for the quantum information and quantum processing community. We show that indeed, if you choose a computation well defined, you can, on that computation, which of course we cherry picked, we could outperform a classical computer. So the paradigm is that there are certain computations, not every computation, there are certain group of problems that can be done with quantum processors faster than classical processors than your common computers. Not everything. Commonly people ask, usually they ask like, is this going to be in our house? Probably no. Is it going to be in our pocket? No. You know, you do an image search, or you do some, you want to know if two molecules bound together, so you submit a job request to a computer which is kept at a low temperature. That would be our processor, and we provide the answer. So it's very unlikely you're going to have this processor in your house, although you can hold it in your hand, but there's not much desire to hand it to people. That's not how it's meant to work at the moment. On slide 3, I show you how this processor, or one of the typical versions of them, look like. This is a processor made when we are at UC Santa Barbara, and done by a grad student, Charles Neal. Um, that's what I can publicly share. Our new processors, I would have limitations to share exact design of them. So what you're seeing here is a pattern of aluminum on a piece of silicon or a piece of sapphire. But then we Photoshop these colors on them, we Photoshop them with colors, so you can know the functionality of each piece. Otherwise, it would be a very boring picture of black and or gray and black lines. So essentially, you are seeing 9 qubits. They are painted red, and they are oscillators, resonators, I don't know, depending on your background. You can imagine these objects can have in 2 configurations, configuration 0, configuration 1. And then you see some funny figures, some figure 8 or 2 squares between these qubits. These are called couplers. Couplers allow the qubits to interact with each other. And then on top of them, you see a meandering line. And that is a resonator which reads the state of the qubit. The rest of the picture is just wiring. There are some wires come to the qubits, and they excite the qubits. Then there's a wires to turn on and off the coupling, and there's a top two wires, that blue ones, that are coming and sending signals, so you can read the states of the qubits simultaneously. That's a good moment to take questions to be sure you understand how this object is look like, or what you're looking at.
A quick question: Are the implication from the figure is that only the adjacent qubits are coupled, or is it?
Exactly. Is a major business, is a major challenging business. You can imagine if you could, so you are seeing 9 qubits is a 1 by 9 by 1 grid. Um, if, if you could connect qubits that are further apart from each other, you could increase your computational power. That's very important. More connectivity, more rich grids, and that is important. However, you can imagine that you're seeing that we are living in 2D land. And in 2D land, connecting things without jumping on top of each other and creating confusion, we call it crosstalk. Imagine you want to connect two things that are not next to each other without affecting anything in between. That's very challenging. What you could do, and it's done maybe I don't know, in conventional processor makings, is they put a layer of oxide on top. They just oxidize, and then they put wires, and then oxidize again, and then they put wires. However, we cannot do that. These oxides are very lossy, they are very much killing the fragile quantum states, and we should avoid them by all means. The whole, maybe someone should ask me, okay, this is it. Why can't you just make millions of them and go and make a quantum computer and be done? The problem is in the interfaces and these tiny corners that the fabrication is imperfect, and you have oxide or junks, and these junks kind of ruin your quantum state and kill the whole quantumness of the device. And that is why putting a layer of oxide is a big no. There's tiny amount of oxide at the end of these red stripes, which you cannot see. And even that little tiny amount is really detrimental, but there's nothing we can do about it. So building a quantum computer comes to the challenge of preserving a fragile quantum state, which is fragile to all sorts of disorders.
So sorry.
Go ahead, Tuan.
So I heard that there's two approach to deal with that problem, and one is decoherence, and the other one is error correction, right? Could you give some comment about the
They
error correction approach? Thank
they
you.
they come together. They maybe 20 years ago, people realized that the decoherence issue, which I described, is not going to go away. Qubits are going to be making errors. The idea of error correction is that if the frequency of the errors occurring is very low, is very infrequent, errors happens during computations, we can identify them and then account for them and fix them. The idea is that imagine as you do computation with these 9 qubits, you had a layer of qubits next to them or another row of qubits next to them, and you use them as watchdogs and keep measuring those qubits. And if any of your computation qubits make a mistake, your watchdog qubits would register that mistake. And then at the end, you look at these watchdog qubits, they call it measure qubits, of course, not watchdog. You look at these measure qubits that has been frequently policing the computation and watching over the computation. And if they tell you that something gone wrong, you go and try to fix that. The notion of error correction, the notion of decoding, all of that rests on the fact that if errors are infrequent, we can correct for them.
Um, Pedram. This is
Hi.
hi. This is VTR, and I was going to ask the same question, so this becomes a follow up. So
Sure.
for error correction, I believe it gets around the no cloning principle, right? You can like how do you is it also a solution to scaling qubits
Uh,
or
well, yes. Uh, yes. Yes. If we want to make lots of these qubits, put them together and do a computation, you can, but you're going to get a very meaningless result. The fragile coherent quantum state is decohered and you are not going to get anything interesting. And it's not a really computational platform at that moment. Um, so before you scale up, you have to have a good error correction mechanism in place, and you have to be sure your hardware does not make so many errors. I think these come together. So brute force scaling while your qubit quality is not good enough is not the answer. You have to make good qubits first.
So I have a follow-up question to that.
Sure.
So given that you were describing that these are sort of macro scale parts that have been
Yes, yes,
put together, and
yes,
then you should not be using reactive oxygen species type of things to link
yes,
these parts together. Is there, or rather, I'm sure there are 3D printed, fully integrated systems, maybe a CNC, or has this sort of effort been
yes,
taken
yes,
into
yes.
experimented on the nanoscale so that you don't have to brute force it, you don't have to deal with.
No, yes, yes. Of course, you can imagine the whole basic idea of qubits and things coupling them and whatnot can be done very differently. Any quantum state, you can do computation with atoms of hydrogen if you could get them to interact with each other, and you can control them and manipulate them and address them.
They don't play nice together.
No, no, they I think 1D line of hydrogen atoms is unstable. They just buckle up together. Um, but can I make aluminum 3D with CNC machines and whatnot? Yes, people have done that. But what you're seeing in here is more advanced in terms of what computation. The biggest algorithm that performed that has been successfully implemented comes from our hardware. There is no fundamental reason to believe trapped ions or others are not capable of doing it. It's just there is lots of technological challenges and we have been ahead of the game. So all these ideas are possible and have been shown in a smaller scale, but usually the challenge is when you start putting larger things together, things get really complicated, and we just have been staying ahead of others.
Scaling up does
So,
tend to be a persistent issue across all sorts of sectors of technology.
Exactly, exactly. Well, I can speak for quantum processor makings, and yes, it's not easy.
Hi, Pedram.
Is there
Next to
any?
you here, Abyss here. So, um, first of all, I'd like to thank you for sharing your story. I think it's um, uh, pretty inspiring, and I think like it's kind of harrowing that experience that you have to go through. And I'm glad that you're here with us to share experience. That being said, I do have a question for you. So, when designing these chips, do you actually follow the same kind of standard when design manufacturing silicon chips? That's like, do you apply some kind of photolithography or some
Exactly.
kind of
Yes,
vapor
yes.
deposition? Okay.
Yes. Yes, we borrow many techniques of sputtering aluminum or nanolithography fabbing, or it is mainly microstates. There is some closer to nanoscale parts too. Uh, and then when it comes to oxide, we just disagree with each other. A classical processor making can easily put oxide, and at that moment uh, we just we just don't get along anymore. But we do use the same type of devices in clean rooms that silicon industry is using.
I think I
So
have a.
just
Go
uh,
ahead.
sorry, I have so follow up. So I was in this room, actually, kind of in a different room where we talked with some metamaterial researchers, and they were kind of employing some kind of like electron beam kind of etching mechanism for precision. So I'm just like curious if that's also applied here. Of course, like you kind of probably have, mixture of different, your substrate there, and then like have oxide layer or something like that. But I'm just
Yes.
curious, like if for more precision, do you apply that sort of
No,
thing?
no. The precision, to achieve precision, we do not do these. Look, these are optical lithography, and if an object, if the qubit is not at the frequency we like, all the wires that you can see coming from below would be able to adjust them. You need those wires anyway. So, and these are going to change frequencies and couplings and whatnot. So if you don't hit your expected value, you can apply voltages to these control lines, and you can move things around. So we don't. It's better that you don't mess up with the chip by processing and processing. You try to reduce the number of the fabrication processes you would do. That would be the best. So we try to do minimum processing, and but yeah, the precision is not that big of a deal. Trying to cook up recipes that do less processing, that is the challenge, I think. Um, but also, let me admit, I was going to clean room. I was actively going to clean room, and I was not good at it. Uh, and then, uh, and then I remember the night that my daughter was born. I was about to go, and my wife called, and I end up going to hospital. That was 2013, and that was the last time I went around clean room. So probably I don't know as much as some of you anymore. I haven't been involved in the conversations actively, so I'm very much talking from memory. Um, should I move on? You guys have lots of good questions, I have to
No,
say.
I had a quick
Yes,
question. First of all, thanks for answering my question that I asked a
Sure.
couple of minutes ago. I wanted to hear from you, like just a little bit of background about like time crystal, and since I'm seeing the slides. And
I'm gonna get there. That
okay,
that that's
okay,
that's that's what I'm here
okay.
for.
Sorry. Yeah.
No
Thank
worries. So if we look at the slide 4, um, you would see what we mean by computation and what we mean by operation and what we mean by errors. Um, you can see this layer of qubits, this 2D grid of qubits. We can apply pulses to them, and that's what we are trying to show in the lower panel. Um, that if you open that manuscript that I was showing on slide 2, you would see this is one of the figures there. On the left, it shows you the layout of the qubits, and then there is a time sequence, cycle 1, cycle 2. This is the operation that you apply on the qubits. These are the voltages, these are the pulses that you send to the qubits. You rotate the individual states of the qubits, you let them interact, and this is usually how the operating of the qubits look like. On the top, we are trying to show you how much error we have. This is a histogram, but a cumulative histogram. Um, it shows you the typical errors that we have over every individual component used. And if these errors were 5 times, 10 times better than what we have, we would be rushing to scaling up. And if this error were 10 times worse than what they are now, there's absolutely no hope of making anything out of them. And they're just good enough, they're not very good, they're not very bad. They're just borderline that allows those error correction ideas to work. They're not safely below the threshold value. But it's very important that always ask from quantum processor people that what is the distribution of error on their processor. And we are showing how single qubit operations have error, 2-qubit operations have error, how much reading the state of the qubits have error, and it's very fundamental to our business, and it's people's life goes into addressing and fixing these things. Okay, so the computation we did, which made us headline news, and in fact, I think we were on the cover of New York Times too, was on that slide number 2, I showed you the paper, is that you run this sequence and you ask what's the outcome. And if I tell you the gates, the operations, you can predict the outcome with some probability. These are bit strings coming out, outputs, and then there's certain probability to them. And you can ask what's the probability of each of them. And the claim we had was that our processor can predict that outcome faster and better than any classical process, any other way of doing this computation. And when this processor when of course things get really large. But you see, the problem is a bit contrived. We of course knew we're going to beat the classical computer in this problem. So if you go to slide number 5, I'm showing you the possibilities and cases that we could do something interesting with these processors. So you have to have a little more number of qubits, and you have to have much better probably operations. The vertical axis is scaling logarithmically or exponentially, and the horizontal axis is just linear. So you need a little more qubits, maybe 100 of them. The experiment I show you on the slide 4 had 53 qubits, and you may need 100 qubits or so. The computation would be very valuable if you could do it with high precision. The idea of error correction that came out is that was asked a few minutes ago, says that you don't need to have very good qubits. You just need the qubits to be maybe 0.001 or so good, and you just need lots of them and make logical qubit and such. So that's a different paradigm. But the supremacy experiment, the time crystal I'm about to explain, all of them coming in the category of what we call NISQ, noisy intermediate scale quantum processors. Something that you don't do error correction, but you rely on the quality of your qubits to be really good to do a computation with them. And time crystal is in that category. If we are good, I can go and show you the basic principle of the physics underlying time crystals. All good. Okay. So what's the news? Someone was just telling me that yeah, I see lots of coverages and news, and Google did this and that, and what are they coming from, and what do they mean? Here is the idea. If you get a collection of atoms and you cool them down, they form a crystalline structure. This is coppers would do. This is what iron would do. This is ice is doing. And this spatial order comes in many different flavors. It could be, you could see a stable liquid crystal. You could see ferromagnetic ordering, anti-ferromagnetic ordering. These are systems of lots of particles, lots of degrees of freedom. And instead of making an amorphous collection, they form a periodic pattern. They're much more comfortable to make an ordered state rather than disordered state. So they have periodicity in space. You know a row of atom, you know if you move certain distance, you get to the next row, and next and next and next. So there is a spatial pattern. There's a pattern in a space. You say, can I see a system that shows pattern in time? Meaning it does something, you wait for a moment, and then the next cycle comes and does the same thing again. Our solar system is doing that. A child on a swing would do the same. It just goes back and forth. So there is a periodicity in time. You see the position, you know things, you can predict that, capital T seconds later, it's going to do the same thing, and so on and so on. A clock, a watch is doing that. They are oscillators. But with the top row and bottom row has a major difference. And the difference is the following, is that these systems on the lower row are very few particles, very few degrees of freedom. A child in a swing can be explained by one simple angle. A clock, can be explained. There's a part is made of many atoms and molecules, but they all move together. Is not have that many degrees of freedom. You might say, okay, that could be accidental. Maybe if I look harder, I can find the systems of particles that show periodicity in time. The challenge is that you would not find that. That is very puzzling, and that's very interesting. So I showing the same concept on the right side of the slide. What I'm saying is, if you have a crystal, let's say, and then you poke a corner of it, or the corner of it get heated up, or I don't know, if you just wait, it's just going to come back to where it was, a stable pattern, periodic in a space, all very nice. But imagine a bunch of pendulums are moving, and they're interacting with each other and showing a periodic pattern. What I'm claiming is that when you come back and look at it some later time, they would be very disordered. They would not show a very nice periodic time pattern. Or if they are doing it, is because the extra entropy generated has been extracted from the system. Or if you come back and see still they're doing it, is because it's very fine-tuned to some very fine value of parameters, and if something changes a little bit, it's not stable. So the system of interacting particles showing periodic pattern in time seems to be unstable and hard to find. But this is not against the fundamental laws of physics. So if you look at the top of the slide, we translate this challenge into a definition. We say, can we find a system which you see indefinite oscillation in a system of lots of degrees of freedom in isolation? And that is the definition of time crystals. Maybe it's time to take some questions.
I have a quick question.
Sure.
You described this pattern that is time dependent, and depending on the variables, it could be chaotic or it could be cyclical. And I wonder how the gravitational constant figures into this, given that these simulations or real experiments are based on physics as we understand it currently.
Well, when you're doing a classical system, of course, you have to consider a gravitational force. But for quantum system, we usually ignore them. The interactions and whatnot that we have is many orders of magnitude stronger than that. But the claim is that you look into classical system, you look into quantum systems, you are not going to find a system of many degrees of freedom which have a stable oscillation in time. And that, but it's not impossible, so we call it a definition and start looking for it. Am I answering the question?
Yes, and now I have a further question. What is the constant of a qubit?
What do you mean?
I like if there's a gravitational constant on Earth and it changes in different parts on different planets, is there a constant for qubits? Maybe this is a far-fetched question.
The qubits are not, the state of the qubits are not affected by gravity with the precisions that we work in. How a quantum system is affected by gravity is not known, but we know even if there is some effects is negligible. The qubit would be interacting with each other, they would be decohering out to their environment in much different time scales and energies than what gravity would do to it. So we totally ignore gravity in these scenarios.
I guess my question is there a fundamental number we should know about qubits? Like, if you were to
No,
say
no.
qubit as, okay, right on.
You can ask what is their oscillation energy, or how often they how they oscillate, or how much they interact, and these are in the gigahertz and megahertz range energies and time scales essentially.
It
So
also is dependent on the level of energy that's flowing through the system, no?
yes, but we set those parameters. Because we want to interact with them with commercially available electronics. We set them to megahertz and gigahertz, and we can manipulate them. So all the dynamics I'm about to show you happens in the let's a few microsecond time scales.
Okay, that was going to be the question I was going to ask about the time scale, microseconds. Thank you.
For us, you can have a little slower qubits, different systems, and then different slower interactions, and it could maybe get to milliseconds and such. For us, we are at most, I don't know, we get to 10 microseconds or so. Okay. Um,
Can you
I,
repeat your definition of time crystal, please?
it's if you look at slide 6, on top of it, you see the definition. So it has few components. It has to be system of many particles. Technically, a child on a swing can go forever, but has only 1 degree of freedom, and that doesn't count. You have to have many degrees of freedom. These many degrees of freedom, many particles have to interact with each other. Otherwise, you're defeating the definition, the purpose. And it has to be isolated. You should not really remove entropy from the system. It should be isolated. And technically and theoretically, it should be stable, meaning that theoretically it should indefinitely oscillate. Can such a system exist? That's the question. Is that
I have a couple of questions,
sure?
and welcome Pedram from my motherland. So I'm in slide number 4, actually. You just mentioned about pulses, and I was just wondering, the pulses mostly produced through the row or column or time? Which one?
You can address columns and rows at the same time, um, and you can simultaneously address and send pulses to several qubits at the same time, and then you can go and change the schedule and say the next instant of time, the next cycle, I'm going to manipulate and send signals to these sets of qubits. And that is that pattern of squares and dumbbells, the color ones, is trying to show.
Okay.
Say that as a function of time, we're going to talk to these qubits, and then we're going to talk to those qubits.
Sure. And in a slide number 2, is there any, a specific reason that you just chose 0.5 millimeter for the redot part?
Yes, yes, that's a good question. We want the it's the electronics that available in the market, and it's just and is affordable in an industrial sense, and commercially you can work with them, and comfortably you can play with them, is sets the frequency of these objects, and frequency essentially is set by the dimension and size and how big they are. You can make these objects smaller, the frequencies would go higher. Trying to address them and work with them would be much more challenging to have proper electronic devices.
Sure. And in a slide number 6, in a stable position that we
Sure.
have a changing because we have a perturbation, and after some time, is there any G produced in between this process or not?
What do you mean G?
That was part of the formulation that you just put it there, and in further, I mean, when you go forward in forward slides, you have a G
Ah, no,
as
no.
a
I'm saying that usually don't worry about that. Let's look at this slide number 6 in a more abstract than the exact formula I have. Um, I think what I'm saying is that what I'm saying is that generally an interacting system of many degrees of freedom is not stable in time. If you see a temporal order, you come back and look at it this instant later, probably is gone. Many different reasons. Maybe let's go to a slide number 7. I'm saying that look at the top part. I'm saying that you see a pattern. You see you have a closed box, and in this box you have some pattern. And look, you have certain particles and you want them to move between these two configurations. Note the color of the red particles and blue ones are different. You want these to keep going between these two configurations forever. But and they can be anything. They can be backgammon parts or anything you like. Molecules, atoms, big, small, doesn't matter. The most likely scenario, according to the second law of thermodynamics, is that the entropy increases and you get a disorder pattern. But the second law of thermodynamics doesn't say the entropy has to increase. It just say it cannot decrease. So if you could go between these two patterns, the entropy would not increase, and it's not violation of the second law, but it's very unlikely scenario. And we are trying to see if we can stabilize that very unlikely scenario. So on the heat death and the disorder configuration are very likely scenarios. And we are trying to see if we can beat them. Of course, it's not any violation of the laws of physics, it's just hard to avoid. So on the lower part of the slide, you get a bit technical. There are a couple of proposals how to do it. They showed that you cannot do it easily, so you have to go to more advanced configurations. And when you come to a slide 8, here, the definition that I was just asked, what's a time crystal? A closed system that indefinitely oscillates, of many particles that indefinitely oscillate. That definition, if you pay close attention, has maybe 4 segments to it, and those 4 segments can translate into 4 concepts that we experimentally explored. So you can see a bit more technical, longer definition written, stemming out from the definition I just mentioned, and you have it on slide 6. You can see the definition get a bit longer if you really try to spell it out for this configuration. And but the gist of the paper is that we dissect that definition and we try to provide evidence for them, and we try to show how these things are feasible and whatnot. That is the gist of the paper. From here on, it's very technical. Maybe I spent a few minutes so you can maybe walk it through yourself. The way it works, again, look at the slide number 9. I'm showing a pulse sequence again applied to qubits, how each pulse is doing. We record what it's doing, and then we turn the pulses one by one. Then you get to slide number 10. You see the effect of them when more and more you put together, and you see oscillation, the autocorrelation A Z0 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 ZT. It shows the oscillation. You manage to stay at the corner of the qubits and measure its response, and you see kind of up down response is indicative of the oscillation. So in fact, in the lower part of the slide 10, I'm schematically showing what the qubits are doing, that the actual behavior is far more complicated, but you can take it that it goes between two configurations. If you look at it, there's a pattern, the pattern changes, but it changes back. So patterns at cycle 1, 3, 5, 7, it shows one pattern. At cycle 2, 6, 8, 10, it shows different pattern. Slide 11, I think, unfortunately, was animated and you're seeing only half of it. It meant to discuss the notion of isolation, uh, how we argue for isolation, because our system at the end of the day is not really isolated. Slide number 12 talks about notion of localization, notion of stability. That you can see that they look at the two color cases. One case, as a function of time, the system is not stable and diffuses. That yellow line diffuses around. Another one, as a function of cycles, they think the perturbation stays localized. These are very technical signatures that we had to prove, and the rest is about scaling to larger systems and whatnot. It would be hard to explain more briefly without going to technical stuff. Maybe I answer questions on these later slides. That could be maybe constructive.
Quick question, is the decay that you're showing in the amplitude of the oscillations, is that energy bleed off, or is that accumulation of error?
Oh, that's a very good question. That is a very challenging and is a heart of the dispute that we had to overcome, and we provide our best evidence. You could argue one way or another. Yes, we have to distinguish between what did you call bleed off, between losing energy to environment, which is violates the definition, and some internal dynamics that could lead to that too. So unfortunately, you don't see the lower part of the slide. It's it meant to show that what we are seeing is stable as soon as we remove the effect of, I think, what you call bleed off. So we say there is an internal dynamics and there is an external dynamics which is undesired, because we try to look at the closed quantum system. And as soon as I could manage and argue to remove this decay down to open quantum system effect, down to the fact that my system is actually not closed, if I could manage for that, then bingo, the signal is stable. I think you can see that on the online version of the paper. I hope my colleagues make this article open access too, so you can go to website of Nature and see it directly. Yes, sorry, it's half a slide, but it meant to distinguish between those two things, and it's really a big deal to show that this decay is not, it can be compensated so long as soon as you remove the open quantum system effects.
And so that's by normalization, that's what
Yes,
gets you
yes,
into the
yes,
tens of microseconds. I mean, that's your
yes,
time
exactly, exactly.
limit. And then just kind of a tangent, no
Sure.
pun intended. Um, I'm sure there's discussions about these systems in space. Would that likely improve any of the, the decay properties or the decoherent?
Like sending the whole thing to the outside the planet,
Yeah,
space.
on board satellites or whatever.
No, no. Unfortunately, no. Unfortunately, the chip itself that you are looking at the slide, what was it? Slide 3. The whole ugliness, the whole undesired effects are right there in that construction. There are some other effects like cosmic rays and whatnot hitting this chip, but they're minor, and you don't get much better if you go outside the planet. This is a big fridge, and no matter where you go, you have those effects with you. You're not trying to. Um, um, there's no gravity is not your biggest enemy or has little effect on these things.
Well, I was just thinking more about the vacuum, but then, the exposure,
No,
everything's.
the vacuum we can achieve on at these low temperatures actually is as good as outer space probably, and is vacuum technology is well established, is not that hard, so, and the complication of sending some instrument out there, it kind of um, um, doesn't justify it.
You
Last,
can definitely achieve a better vacuum on Earth in a chamber than you could on the International Space Station, for example.
I think so. It's not. Is what it get exposed before it get to vacuum. I think when it gets to vacuum, is not a um, is not a big deal. Let me make two things very explicit. Low temperature. This is happening at 10 millikelvin. So Kelvin. This is 10 millikelvin above absolute zero. This 10 millikelvin is established practice, is not challenging. This is from 1980s. We know how to do these. Vacuum also a very established technology, and these are not the biggest thing. I think material science issues, materials that goes into these chips, as I'm showing in figure 3 in picture slide 3, those are really bigger issues that we have to deal with. But maybe I give you benefit of the doubt why you get confused, because sometimes you open articles say, oh, we did it at room temperature. People make those claims that they could find a two-level system that they can use as qubit at room temperatures, but they are really not sure, and they can get some attention, but I don't think that's the biggest challenge. Vacuum technology, low temperature technologies, way established, and these are really not big challenges. The challenge is to do bigger and bigger algorithm and reduce your errors.
yeah, okay, 10 millikelvin answers a lot. Are you able to share the composition of the material of the qubit, or is that proprietary?
No, it's just what you're seeing on slide 3. You can start with a sapphire or silicon. Sapphire look like a glass, essentially. It's a just better version of glass. I think it's aluminum oxide. I forgot. I think so. Um, and or silicon, just something pure, not that many impurities in it, and then you just do several layers of lithography. So what you're seeing here is just aluminum and some aluminum oxide some places. So that's it. There is no secret in this sense. We are not using any special element. However, the devil is in the detail of how we do these lithographies and how we process them, and which layers goes before what layers, and how we are showing that the voltage across is uniform, and that those kind of details, which I cannot share, which I don't know even to begin with. So it's easy.
Thank you.
May I ask a very arrogant, like ignorant question, probably because I'm a neuroscientist and not a physicist at all.
Sure.
Um, so when I think about the time crystal and that it has to be very isolated in order to perform to this patterns of oscillations, um, what does it mean in the bigger picture? Does it mean our universe is not an isolated system, and or does it mean only that we don't have the time scale of data that we can see a very a pattern of oscillations in order to test if it's an isolated system or not?
Um,
Or does it have nothing?
I don't.
Sorry.
I don't know. I don't know if anyone took it that far. But look at the slide 6. We are saying that can a closed system go indefinitely oscillate? I don't, well, I mean, universe, I don't know if it's open or closed, but doesn't enter the conversation of small quantum systems we are discussing. The question by itself, as it written on top of a slide 6 as a definition, is by itself is interesting. Can you find a system, and you can see my pictorial kind of challenge of it on the slide 7, that can you find a system that keeps going between two states indefinitely, and it has many particles in it? I don't know. It doesn't have any. No one ever thought about it in the context of openness or closeness of universe. Those are big questions. But
It's just because instead of having the Big Bang, I read in Carlo Rovelli's book that it's probably more likely that we have the Big Bounce. So always a state of expanding universe and then imploding again and expanding. So it would be kind of this two-state system of the whole universe.
yes, yes. But I'm saying we with what we are doing, or these theories that these time crystals are built on, I cannot see the shedding light on those questions. Was it Big Bang or is it Big Bounce? Those are very big, valid physics questions and discussions, but but the setting that we are talking in here is more about second law of thermodynamics and fighting entropy in this sense that I mentioned. Uh, yeah, I don't know how to make anything bigger than that out of it. And the theories that work on these time crystals also never try to relate or make a leap connecting to those concepts.
Thank you.
Sure,
Sorry.
no worries. Uh, yeah,
Oh, hi. Thanks, uh, Dr. Rohan, for
sure.
sharing your uh, fascinating and advanced research with the Science Society on Clubhouse. Really appreciate it. As an engineer, I would, I think the physics behind this beyond me, but I'm just trying to get the basics of it from your slides. A few questions, if I may.
Sure.
The Why is, in your definition of time crystal, the number of say qubits matters, or degree freedom matters? Isn't, I mean, good enough to demo that with a manageable number of
No,
them?
no, 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 no. That is conceptually the same as a child on a swing. That we know is stable. That's not a challenge. That's nothing new. Uh, if you hypothetically have a planet orbiting another planet, another star, that we know is stable. The challenge is not that's known physics. No one is perplexed by that. The question is, on top of a slide 7, can we get these two things go between two configurations as they interact with each other and as they have many degrees of freedom? The the stability of a clock of a child swing is not a mystery in physics. That's not the question.
Uh, then would it be possible to specify what will be a threshold of the number of degree freedom? Right now, three body problem is already, unsolvable. Has to resort to computers.
Yeah, yeah. I don't know. I think it's well, theorists talk about many degrees of freedom, but I think usually community says if you have 20 qubits, you have 1 million degree of freedom, and that's probably convincing. Is no, I don't think anyone have a very sharp number.
Yeah, I
We
see.
did it at we did at 20 qubits, which is a million dimensional computational space. 1 million, I think.
I see. Thank you. So to go, follow up on the Serena's question. So is it? I don't quite understand the question. To which figure is it on the slides number 12 that we see in the top left that there's a decay of each qubit and also
No,
shows
no,
on the
the
number
decay.
13.
Everything we measure is decay. But the first thing we showed on a slide 11, we say these decays are because our quantum system are not fully closed, and we can compensate for that. These decays are very undesired, but we try to show down to internal dynamics there is no decay. So if we remove these open system effects, there would be no decay. Is a argument we had to make, and it's very unpleasant, and it's really the weakest point of the work. But everything decays, but the claim is that we can compensate for it.
Everything decays per physics, entropy, etc., right?
Because the system is really not isolated, it's really losing energy to its surrounding.
So in the normalized data set that it shows
Yes.
rather than decay, on slide 12, I believe, um,
Well,
there's an oscillation there in the amplitude. You know what's going on there?
maybe we look at the slide 13. That's a better place where I have the picture of my favorite guy there. On a slide 13, actually, you can see the normalization and correction and such. There is some oscillation in the beginning. If you look at the right side of the slide 13, that oscillation can be, yes, that is down to the physics of it, that there is a little internal dynamics that dies out quickly. We understand that is a well-known physics, and then it becomes more stable at later instances of time. Yes. I'm hoping we can finish in a few minutes. I was not, well, we never discuss how much time, but I'm hoping we can finish in a few minutes, if or I can come back if there's so many more questions.
Absolutely. If we really value your contribution and time, and if you have to go, then you have to go.
Yeah, let's aim
Maybe
for,
one more question. Sounds
no,
like.
we can do to 7:15 my time, a few more minutes. I'm yeah, I think we covered many things, and I don't know, I cannot see how many questions are left, or how does it
I
even work.
It
think
seems like, yeah. Go ahead, Katrina.
I think we covered a lot of questions, and we really appreciate the time you spent with us and
Sure.
the knowledge shared. Uh, yeah, you're always welcome back to share.
Yeah, if
I do have a last question, if I
Oh,
may,
no, no,
ask it.
I can give you guys 5 more minutes.
I have one too.
Sure, sure. Let's do the last 5 minutes or more questions, please.
Oh, really appreciate it. So, so the on the slides number 10, the I think this is the mechanism that I definitely need a few years of physical education to understand. But just to understand the setup, so you started with a system. The relative phase are, you're not controlling that, right? It started with some random relative phase between the qubits, right? And then you do control.
Yes. So the challenge, you should contrast that slide 10. Let me see, with so on top of slide 7, I have a schematic of a system, um, that goes between two configurations, and we are seeing if we can see it. On slide 10, I say that the state of the qubits, it's two configurations, let's call them up and down, and we paint them red and green, red and blue. And then we say that, hey, look, our measurement shows that it goes, whatever is up goes down and then up. And this configuration of individual qubits continue. And that is the data that you see on the right side that oscillates between two values. Forget about the decay part, but it oscillates between two values. And we are trying to say that, yes, no matter what configuration you begin with, this configuration would be repeated at cycle 1, 3, 5, 7, and there is a symmetric configuration that repeats at cycles 2, 4, 6, 8, and such.
I see. So then again, back to the essentially that's the initial state is what I understand. So the number 10, the again the schematics of the experiment. So you're flipping the bits using laser or using voltage, or
Micro,
how do you
microwave pulses. Microwave pulses.
microwave pulses? I see. And so the only introducing like binary coupling is that I don't know if this is a legitimate question. I mean, at each
On top of
at a say, I mean, I get the gist. I mean, for DTC, you have a T, then you get a 2T, right? So that you're doing the microwave wave pulses in period of T cycle and the
on
binary
top
bits.
on top of a slide 10, top left, you see that those sequence, let me try to help you to understand what this sequence is. It says what you should do, you should rotate the qubits. You can do something with the qubits, that's the green boxes. And then there is blue boxes which says let the qubits interact with each other, do something between pairs of qubits, and then you have another type of rotation on the individual qubits. And this is what we do in one cycle with all microwave pulses. And then we are going to record the state of the qubits, and then we're going to repeat it twice and then record the state of the qubits. We repeat these pulses 3 times and record the state of the qubits, and that is the definition of cycle.
I see. Much, yeah. Thank you for that
Sure, sure.
explanation. It's a very great. Thank you very much for helping me
Sure.
understand it.
Okay, thank you again for your
Sure.
time, and
Sure.
come always back to our Science Society Club. And thanks for answering all the questions and
Sure.
sharing your time and knowledge with us. It was a great pleasure.
Sure, yeah. I'm very happy for the opportunity you guys provided for me. I hope this was useful to you all. Thank you.
Yes, thank you so much.
Thank you,
And
Pedram.
Sure, sure. Yeah, thank you, everybody.
Thank you.
Thank you very
Thanks,
much.
thanks,
Yeah.
thanks. Bye.
And everyone, if you like this room, follow the Science Society. We have guest speakers, scientists that do all this very interesting and cutting edge research here as guest speakers. Tomorrow we will have Dr. Mackenzie. He studies very fundamental molecular interactions, chiral molecular interactions in different settings. And the latest paper, he looked at these interactions in the live cell. So it's kind of groundbreaking, very fundamental molecular biology in this case. He is joining us from the UK. And then we'll have on Thursday Dr. Fletcher. He's actually also a theoretical scientist, and he will talk about his latest paper and also book. He's also an author of scientific books, how you can train creativity, and he generated a new method. And then we'll have Dr. Lewis from Oxford University, a theoretical scientist who will talk about, a theoretical physicist who will talk about why evolution favors symmetry. And then on Saturday, we'll have Dr. Gudu Pidenis from Max Planck Institute in Germany. and he will talk about his project in organic neuromorphic electronics, which was really a novel scientific field. So yeah, join us again. Thank you for being here and asking all these questions and making our guest speaker feel welcome. I really appreciate for this great round of discussion. And talk to you soon. Please check out the times, because this week our guest speakers from now on are all from Europe, so it's on an earlier time. Tomorrow is so they are on an earlier time because they are 5 to 6 hours ahead of EST time. So yeah, please check the times, and thank you so much, everyone, again.
Thank you.
Thank you,
Bye-bye.
Katrina.
Thank you, Kat.
Thanks, everyone.
Bye, everyone.
Bye, everyone.